Heatwise tutorial on psychrometrics. This is part 3. So this video will be about the equations behind the psychrometrics calculations. So instead of looking at the chart, we'll actually be doing the math on paper here. Many people prefer this way because it's a lot less approximate than just looking at the chart. The chart can be much quicker and easier and is a nice visual, but now that we have modern computers, many people like to program the equations themselves. So in this video, the equations that we'll be going over are the altitude adjustment. So that's P over P0. So that's P0 being our standard atmospheric pressure. So this is our altitude adjustment for various factors. We will also be looking at the relationship between our dry bulb temperature, enthalpy, and our humidity ratio. And we will not be diving into equations for things like the wet bulb temperature, specific volume, or the relative humidity or dew point temperature, because those ones are significantly more complicated and they're not as useful, and a lot of the math can actually be done with just these three values here. And ultimately we can use these three values to determine our sensible heat, latent heat, and total, which is just the sum of those two. So starting with our altitude adjustment equation, we have P over P0 is equal to 1 minus 6.8754 times 10 to the minus 6 times Z, Z being our altitude, to the power of 5.2559. Bit of an ugly equation, but obviously with a computer you can easily just program this in and determine your ratio. So to get your standard pressure, you would just multiply this by your atmospheric pressure here. So atmospheric pressure in imperial units would be 14.696 psi, but you can of course use metric, which would be about 101.3 kilopascals. So I'm just going to leave that equation up there for now because this is going to play a part in some of the other equations. So moving on to our total, sensible, and latent heat transfer equations. For sensible, QS, we have the basic equation CS being our sensible heat constant multiplied by Q, or airflow, times the difference in temperatures. So for example, if we're looking at an airflow, we can determine the sensible heat gained or lost by taking this equation and measuring our leaving air state and our entering air state. So the only things we would need to know are the airflow, Q, and the sensible heat constant. Now, since this is a constant, we always know this. CS is equal to approximately 1.08. Now, the important thing to note here is that CS is actually a variable, or not, it's not a variable, but it can change depending on certain factors. So 1.08 is assuming perfectly dry air. As humidity is introduced into the air, that value actually does change, and some people will estimate it at about 1.10. Now again, this is still going to change a little bit further as you use your altitude adjustment. So with our altitude adjustment, we can change this value basically by just multiplying by our P over P0. So our actual CS value has to be adjusted for the altitude, and you can adjust for the humidity as well, although some people prefer to just use the perfectly dry air constant of 1.08. Some people will just increase it to about 1.10, and that's for 50% humidity. As you increase humidity further, that number would increase. However, you can see that from 1.08 to 1.1 represents a change of going from 0% humidity to 50% humidity. So clearly the humidity does not make a major impact on this equation. So our next equation is the latent load, latent heat transfer load, or equation, and this is equal to CL times Q times our change in humidity ratio. So this change in humidity ratio is what dictates the latent heat transfer. So as you can see here, temperature actually plays no role, and relative humidity also plays no role. It's just a matter of how much moisture is pulled out of the air. Now in this case, we have our airflow again, and we have our latent heat transfer constant CL, and CL is equal to 4,840. And our third equation for total heat transfer is our QT, and this is equal to CT times Q multiplied by our change in enthalpy. In this case, CT, our total heat transfer constant, is equal to 4.5. And of course, the CT and CL values are subject to the same altitude adjustment that the CS value was subject to. So we have to adjust all three of these values for our altitude based on that equation we had from the start. And then these can be applied. So you could easily create a spreadsheet where you have all three values and plug in a simple Z value and get your resulting CS, CT, and CL constants for any process at that altitude. And one more thing that's important to keep in mind is that for any psychrometric heat transfer process, you're going to have only sensible and latent heat transfer, which means that QT is actually equal to QS plus QL. So as long as you know your airflow and you know your entering and leaving state, you can just use any combination of these variables to determine all three of QS, QL, and QT. So if you knew your entering and leaving temperature and your entering and leaving humidity ratios, you could determine your QS, QL, and QT without knowing the enthalpy first. If you knew the enthalpy and the temperatures, you could determine QS and QT and therefore deduce QL or any other combination of these. You don't need all these variables to actually determine all three of QS, QL, and QT. They can all be determined as long as you know your airflow, as long as you have your altitude adjustment. You can use combinations of temperatures and enthalpies to determine your final state and your total heat transfer. So the last equation that is really important to know in this context is the relationship between enthalpy, dry bulb temperature, and humidity ratio. So this relationship can be described with one simple equation, and that is H for enthalpy is equal to 0.24 times your dry bulb temperature plus W, your humidity ratio, times 1061 plus 0.444 times your dry bulb temperature. And now this equation does not need to be modified with your altitude adjustment. This one is just the same for any elevation. So this is a really nice equation to have because, again, you can deduce one of the three variables from the other two. So for example, if you knew some entering state 1 and you have your, let's say, dry bulb temperature and humidity ratio, you can then determine your enthalpy. And if you had your state 2, and let's say you knew your humidity ratio and enthalpy, you would be able to deduce your dry bulb temperature. And in either case, you don't even need to go to those steps. In either case, you can determine all three of QS, QL, and QT. So all your total heat transfer values, so your cooling power and your heating power, can be known based on entering and leaving air states through your air handling unit. There is, however, one more very important concept, and that's with the mixing of two air streams. So with the mixing of two air streams, you can determine both the enthalpy and the humidity ratio through a weighted average of each. However, that does not exactly apply to the temperature. So the weighted average has to be taken on a mass basis. So we have our mass flow rate, which is equal to our volumetric flow rate Q over our specific volume. Your specific volume can be calculated, and it can be determined through your psychrometric chart. However, the specific volume does not change that much depending on temperature and humidity. It does change, however, the changes are fairly small. So you actually can take an approximation of your weighted average with just the airflow value in terms of CFM. So determining your mixed air values for H and for W. So we can take H would be equal to M1 H1 plus M2 H2 over M1 plus M2. And that is approximately equal to Q1 H1 plus Q2 H2 over Q1 plus Q2. Again, there's no altitude adjustment for this equation. It just is what it is. So that's just a weighted average by mass of your enthalpy between your two airstreams, which is approximately the same as a weighted average between the volumetric airflows of your two airstreams. And the same goes for W. So this would just be M1 W1 plus M2 W2 over M1 plus M2. And that again is approximately equal to the same equation, but with our volumetric flow rates, Q1 W1 plus Q2 W2 over Q1 plus Q2. So if you're mixing two airstreams, you can, if you know the incoming state of one, you can determine the incoming state, of both, you can determine the incoming state of the mixture, because in any case, as long as you have two of the values, either enthalpy or humidity ratio or dry bulb temperature, then you can determine the third. So if you have two at state 1, you know the third at state 1, so you can always know H1 and W1 and H2 and W2 as long as you have two pieces of information at each state. You can then determine H mix and W mix, and then you can determine your mixed air dry bulb temperature by rearranging that previous equation, the enthalpy equation. By rearranging this equation, you would get T mix is equal to H mix minus 1061 W mix, so we're running out of room there, over 0.24 plus 0.444 W mix. I apologize for running out of room on the edge there, but once you calculate H mix and calculate W mix, you can get this value T mix by rearranging that enthalpy equation that was the relationship between temperature and humidity. So this equation here was just the rearrangement of H equals 0.24 dry bulb temperature plus humidity ratio times 1061 plus 0.444 times your dry bulb temperature. Rearranging that, we get this. So to solve for dry bulb temperature. So this nice relationship between enthalpy, humidity ratio, and temperature allows you to determine entering and leaving states in their entirety on your psychrometric process, as well as the total power needed to achieve both cooling and heating for sensible and latent portions of that heat transfer process. So that's the end of our part 3 psychrometric tutorial for our heat-wise psychrometrics. So we'll see you in the next video.